Welcome to my BIGSS 2020 presentation. This is Ongun from IMEC Leuven, Belgium speaking. The topic of this talk will be our high-resolution on-chip fluorescence imaging platform. I will start with the motivation for fluorescence imaging using photonic integrated circuits, which will be referred to as PICs from now on. PICs combine optical components such as modulators, waveguides, and filters on a chip to make a circuit. You can see a waveguide and the PIC on the top right figures. Waveguides are used to route the light through the chip in PICs. The main advantage of a PIC fluorescence imaging platform compared to a traditional fluorescence microscope setup will be smaller device footprint, decoupling of excitation and detection light paths, enhanced surface sensitivity, and CMOS compatibility. I should note that the excitation is achieved via evanescent field of the light confined within the waveguides. And this is what makes the technique surface sensitive, analogous to total internal reflection microscopy, while not requiring a tedious alignment as its free space counterpart. Moving on to the state-of-the-art chip-based approaches for fluorescence imaging, we see on the top left that there is a lens-free approach utilizing a fiber optic plate. But this method has pixel size limited resolution, one-to-one magnification, and does not utilize the potential of PICs. There are also two PIC-based approaches in which the excitation and detection paths are decoupled. Both examples use free space optics to detect the fluorescence emission via a microscope objective. On the first example in the top right, stochastic techniques for increasing the resolution is used. Although this method gives very good spatial resolution, on the order of 50 nanometers, its temporal resolution is limited due to the number of recorded raw images, and sophisticated fluorescent dyes are required in this technique, which makes it harder practically. The other approach on the bottom left makes use of structured illumination microscopy technique, which will be referred to as SIM. This technique yields a higher resolution compared to its traditional counterpart, since finer interference fringes are formed within a higher refractive index material, which is silicon nitride in this case. Our research aims to combine the strength of the state-of-the-art approaches by having the PIC right on top of a CMOS imager chip with an optical filter layer in between. For fluorescence imaging application, it is crucial to have a material that has low loss and low autoluminescence at visible wavelengths. The material of choice is silicon nitride, and a plasma-enhanced chemical vapor deposition technique at IMEC 200 mm pilot line is established for this purpose. This technique uses relatively low processing temperatures, which makes the full process CMOS compatible, and in turn, it makes it possible to integrate PICs on top of a CMOS imager chip. Before going on to the full integrated solution, we aim to have an intermediate step with an imaging device that utilizes waveguide-based excitation and free space detection through an ordinary microscope objective. This will be the first milestone in our research. To have high resolution, we select an appropriate super resolution technique to bypass the diffraction limit, as each technique has its own comparative advantages and disadvantages. Structured illumination microscopy, SIM, is the best candidate among super-resolution techniques, as it offers around twofold increase in spatial resolution with a modest compromise from temporal resolution. This also makes it less phototoxic and compatible with live cell imaging. On top of that, SIM does not require sophisticated dyes. On the right side, you can see a schematic of how we realize on-chip SIM with 8 input waveguides. Step by step, the procedure is as follows. Coupling of excitation light into the PIC through a grating coupler. Tuning of thermo-optic switches and phase modulators by applying voltage to generate the desired structural illumination pattern with well-defined orientation and phase. Capturing of raw images through a regular microscope objective, and repetition of structured illumination pattern generation for each orientation and phase required. Then, through a specialized algorithm, reconstruction of the super result image. Now I will proceed on sharing the preliminary results. To realize switching and phase shifting through the active photonic components, the chip is electrically connected to a multi-channel DC power supply. On the top left, you can see the photo of the chip with the laser light coupled through the input grating. First, we check if the input light can be routed into the waveguides of interest with the thermo-optic switches on the chip. This is important as contrast of the interference fringes depends on the relative intensities of the two input waveguides selected. In the bottom images, a case with a single port selection is shown alongside a case with a double port selection, which is typical for acquisition of raw CMIM images. The imaging area is populated with 100 nanometer fluorescent beads. The GIF image on the bottom right depicts the selection of single waveguides in succession for a 16 waveguide device. Next, we move on to controlling the phase of the generated interference pattern, as having a well-defined phase is crucial in correct separation of frequency components from raw images. The left micrograph here shows individual and clustered 100 nanometer fluorescent beads within the imaging region. We focus on one of these clusters and plot the intensity of fluorescence emission as we sweep the phase by electrically actuating the thermo-optic phase shifters. We expect to get a sinusoidal curve as the interference fringes are sinusoidal in the first place, and this is indeed the case. So this confirms that we can shift the phase as we expect. In conclusion, we demonstrated that on-chip structured illumination microscopy is possible with thermo-optic phase shifters for pattern and phase control. The device geometry allows realization of interference fringes with different orientation and frequency. Having verified the interference fringe formation and pattern phase shifting, the next step is the experimental realization of on-chip structured illumination microscopy. Thanks for your attention.